Okay, so I'm going to do a little bit of explanation from MaxEnt by using synthetic data. Here I've got a independent variable or covariate that goes from low values around 0 on the left to high values 255 on the right. And then I've randomly placed some points with a bias towards the right side to say that this is better habitat. We take a look at the MaxEnt outputs. The first one we see is our response curve. And as we expect, on the left side we've got 0 for the covariate value and low probability of presence on the right. And then as we go across, we get higher values over here up to 255, and that's where we get our maximum probability of presence. It's not perfect, it's not a step, because I've introduced some random noise to scatter the occurrences across the landscape. In the lower left, we have our response curve, which I'll talk about in a second, but suffice to say that the AUC is 0.73, and the curve goes up nicely like we'd hope for to have the area be greater than 0.5. If it was along this line, it'd be 0.5 and be random. In the upper left, we have a cumulative threshold graph, and I'll talk about that very briefly. The one that's really important is the ROC curve and the AUC that's associated with it. And the way that is calculated, so that you know, is we move along this line from 0 to 1, and as we do that, we are thresholding our response curve, or you can think of it as we're going to threshold it up here, okay, and then we're going to look at the area predicted as habitat given what is above the threshold. So in other words, if we thresholded it here, or let's say down here at 0.5, then this area of the independent variable, or the covariate, would be considered habitat, and that's actually what we've shown here. And then if we move down to 0.2, here we've got the area considered habitat. But notice what's happening is that this is a relatively small area, even as threshold of 0.2, but it contains the bulk of our occurrences, and that's really what we're looking for. And that's what our receiver operator curve does, is as we move along this line and we threshold, we're looking to have a relatively small amount of area, or fractional predicted area, okay, relative small amount of area with a large number of occurrences. That's the 1 minus the omission rate. Omission is the ones that we're leaving out. So we want to have a lot of occurrences inside a small area, and then that causes this curve to go up rapidly and flatten out instead of following this line if it was random, or worst case, being flat, where we're saying that our model doesn't actually predict the occurrences, it does the opposite. That doesn't happen too often. This cumulative threshold is a bit more obscure. I'm not going to talk too much about it. It's not used very heavily, but suffice it to say that it thresholds along this line, along diagonal, and then on this side is the amount of area, and we want to see, is this curve going this way? And then along here you've got your training data. When you have training and test, we're looking for those two to be fairly close to this line. There isn't a huge amount of variance between the test and the training data. But again, it's a secondary curve compared to the others. Okay, so omission rate, proportion of points left out of the predicted area. That's why we talk about 1 minus the omission rate. That sensitivity are the ones left in the predicted area. Fractional predicted area is a portion within the thresholded area. And then specificity, the proportion area outside the threshold area. Now these sensitivity, fractional predicted area, specificity, omission rate, these are things you'll see in other areas of statistics, and I'll pull them together in a second. So here is a receiver operator curve, okay, and really high AUC of 0.95 for a model that I created, and that's the area under the curve, which is the primary measure that we use for MaxEnt. And the idea here is that if, as we threshold the model, we want to have a small amount of area in our study area, a small percentage of our study area, with a large number of sample points in that same area. Okay, and that's what causes it to go up like this. And that's how AUC is calculated. Okay. Now the best explanation that I've seen for all these different values comes from this chart, which takes into account what we're really looking for in this case, and this is true in binomial models as well, is really looking to say, do we get true positives? Do we get true negatives? In other words, do we say that this is habitat and it is habitat or has occurrences in it. And then for the other areas, do we say that that's not habitat and there's very few occurrences there? The errors would be false positives, okay, where we said the condition is actually negative, but it tested out as being positive, said it was habitat when it wasn't. And the opposite of that, where we have a false negative, we say it's not habitat, but it actually is. And there's a lot of different terms, and different disciplines use different ones from this graph, and this is just this great chart that I found on Wikipedia that brought them all together so that you can use it to reference, like, what is the false emission rate or the negative predicted value, and here it is, and it tells you what the equations are and how it relates to the other ones. Okay, another key aspect of MaxEnt is the idea of features. Features are different types of curves that are used to create the response curve. In other words, when we create a response curve in MaxEnt, it actually creates a response curve from a series of small mathematical equations or smaller curves. It's where when I talked to Stephen about it, I got the opportunity to do that. I asked him, is this piecewise regression? And he said yes. And we talked a little bit about that. That really what MaxEnt is doing is it's creating these curves from smaller mathematical equations, smaller pieces or these features, to create these curves. And then it does a regression on each of those pieces. There's a number of different features. Flat is thresholded, hinge, linear response. Linear is also linear response. There's two of these. Quadratic is the square of the predictor, and then a product. You can actually have two predictors. Again, these are covariates multiplied together, and then there's also binary, so it supports categorical levels as well. And then here we have threshold features where all it has is flat. So this is a response curve that's been created entirely with just threshold features. In other words, all it has is flat lines connected by vertical lines. Linear, there's actually a whole series of small linear lines here. Okay. Quadratic, curves, so fewer lines. It's more capable of modeling complex curves like GAMs are. Hinge, it has an angle to it as well as a curve. Okay, and then product features. And this is product is special in that it's where we're taking two covariates and relating them together. Now, in MaxEnt, the real key is figuring out how to get the best model. AUC does not account for the number of parameters, so we need to use the regularization parameter to control over fitting. MaxEnt will let you know which predictors are explaining the most variance, okay, and you want to use that in your judgment to change the predictors and the regularization parameter to get response curves that you think work well. So as an example of number of parameters, these are in the lambdas file associated with your MaxEnt output, and it can have a huge number of parameters. They're buried in here. It's typical to have hundreds of parameters or estimated coefficients associated with MaxEnt, far more than I would find acceptable. So I'm going to pause there and do another little video.